Good afternoon, and welcome to Oxygen Reduction Systems for Warehouse Storage Applications. My name is Anthony Fontes with the National Fire Protection Association, and I will be your moderator for this session. Please follow the instructions for the Adobe audio setup on your screen. Make sure your speakers are turned on. Your speaker icon should look like the icon on the slide. Please also check your computer speakers. Go to your desktop, and in the bottom right-hand corner of your screen, you can click the image that looks like a speaker and adjust the volume. This webinar is supported by the Research Foundation with 2019 webinar series sponsors: American Wood Council, Eaton, Johnson Controls, Reliable Automatic Sprinkler Co., Intelligent Engineering and Consulting, the Zurich Services Corporation, Victaulic, and Wagner. And this research effort was funded by a property insurance research group consisting of the following sponsors: I will now introduce our presenters at this time. Our first presenter is Dr. Patrick Van Hees from Lund University. He is a professor and head of the Division of Fire Safety Engineering at Lund University in Sweden. He obtained his PhD degree from the University of Ghent in Belgium in 1995, where his PhD was related to fire behavior of floor coverings. His experience includes a time at SP Fire Technology, where he was involved in several projects with respect to reaction to fire of building products, including the SBI method. After moving to Lund University, his research has focused on support for fire safety engineering, especially performance-based design. Important contributions are validation of CFD models, development of engineering models, design fires for cables, functional performance of cables, flame spread modeling, product development tools for building materials, and content. Internationally, he is the chair of the ISO TC92 Fire Safety, the main TC and ISO dealing with all aspects of fire safety. He is also the chair of the International Association of Fire Safety Science. Brian Meacham is managing principal of Meacham Associates, a firm that provides risk-informed performance-based solutions to complex building and infrastructure challenges, conducts building and fire regulatory system capacity assessments, and undertakes research in these and related areas. He has worked with and for governments, NGOs, and the private sector in these areas in numerous countries. Over his 34-year career, Brian has held a variety of positions, including fire safety engineering consultant in firms of various sizes, technical director and research director for the Society of Fire Protection Engineers, principal at ARUP, and associate professor of fire protection engineering at Worcester Polytechnic Institute. Brian is the 2019 president of the SFPE, secretary of the International Association for Fire Safety Science, and chair of the U.S. tag to ISO TC92 SC4 Fire Safety Engineering. He is a Fulbright Global Scholar. Martin Nilsson holds a technical licentiate degree from Lund University, as well as an MSc in risk engineering and a fire protection degree from Lund University. His licentiate degree was related to fire safety of multifunctional buildings in case of antagonistic attacks. After completing his licentiate degree, Martin moved to the insurance industry, where he now works for Zurich Insurance, Ireland, Sweden branch. While at Lund University, Martin researched and published in the area of hypoxic systems, or oxygen reduction systems for fire. And Mr. John Barton is not with us today, but he is also a part of this project. And with that, I will now pass the presentation over to Patrick. Patrick?
Okay, thank you very much for the introduction. So let's start with the presentation on oxygen reduction systems for warehouse storage applications. First, a short overview of the presentation. The main part will be given by me, but also Brian will take over certain parts at certain points in the presentation. We'll talk a little bit first with the reasons why we did this study, then the goal of the project, and then we had 4 different tasks in this research project, and we'll go through them one by one, and I'll finish up with some conclusions. So the review study was initiated by the Fire Protection Research Foundation and supported by the Property Insurance Research Group, PIRG, and it was based on a call for proposals in spring 2018, so it's almost 1 year ago. And we will mainly focus on the results of the project and present them today. And if you still have other specific inquiries or questions and want to know more about the project, the whole report is available at the NFPA website, and I really advise you to download it so you can see all the, let's say, more detailed explanations of some of the outcomes. So the goal of the project was, in fact, to conduct a literature review for ORS systems in warehouses. So it did not include extensive testing or calculations. It's mainly an overview of the literature, what is available, and what type of questions comes out of this literature review. And it's mainly to look into the factors that this test method, which is used for these systems, needs to address in order to obtain the correct emission threshold values at reduced oxygen levels. And that's necessary to have a system which is effective. And also a goal was to suggest potential performance requirements for other alternative tests which are currently available for standard fire testing, if some of them could be applied also. Maybe important to say is that the focus of in this aspect and of this project was, but it was not limited, but mainly focused to fire prevention. And a little bit later in the presentation we'll go through this specific type of item of fire prevention. So at last, also the literature review identifies issues which are connected to, let's say, real-world applications. And we talk here about things like reliability issues, which are related to, for instance, inspection, testing and maintenance, component reliability, operational issues, and relative to this all is to the performance of the ORS system. So that's mainly the goal of the project. We divided this project, as you could already quickly see in the presentation overview, but I'll go through them one by one into 4 tasks. We first started with clarifying the system objectives as fire prevention systems. We also clarify in the next step, task number 2, the impacts of reduced oxygen environments on fire hazard conditions. And then we, in task 3, looked into how we could identify impacts of real-world applications on the efficacy of ORS. And finally, the last task was to identify research needs to bridge gaps between current tests and systems functional reliability in real application, and especially in this case, of course, in applications connected to warehouses. So the first task was to clarify system objectives as fire prevention systems. And before I go maybe into some of the details, I want to quickly explain the principle of an oxygen reduction system. The primary person of such a system is, for fire safety application, is of course to create an environment of sufficiently low oxygen concentration to prevent or significantly inhibit fire initiation, development, and spread. And I know that the 2 slides or the 2 pictures here on this slide give very, let us say, short overview of how these systems work. On the left, you see a system where you have a protected space, and you maybe, which can be an HVAC room, and where an hypoxic air generator will supply the protected space with the correct atmosphere, and it is part then of the HVAC system. In the system on the right, it's done by a specific nitrogen feed into the protected space so that you don't use the ventilation system. And it depends, of course, a lot on where and how these are applied. So it is just principles. So so you either change the ventilation into a hypoxic environment or an oxygen-reduced environment by having this generator in the ventilation system, or you have a specific supply of nitrogen who then mixes with the rest of the normal incoming air. The advantage of an ORS is that you lower, of course, the probability for ignition and possible increased ignition times. And you can see that on the picture on the right, where the red triangle is indicating the probability of fire. Of course, assuming that the probability is connected only to the, say, the ignition, which is indicated also with the levels 10%, 21%. 21% is normal atmosphere. You see that the probability of fire reduces if you go down in oxygen concentration in air. And we know from the theories that around 10% you would not have any ignition for many of the fuels, and that's also quite often used as an inerting concentration if we talk about, for instance, gas extinguishing systems. Another thing is that apart from the ignition, also the heat release is decreased, and you could have a reduced fire spread, which is similarly again. And since it's in principle always operational, because it's there, there's no activation needed connected to the fire. So it's somehow a system which is present there. So there's no action needed from some kind of an detection system, which is sometimes the case in other, let's say, active systems. What is a bit of a disadvantage, if we can call it a disadvantage, of course, but is that the reduced fire risk of ignition that needs to be balanced with possible health effects, and that's given by the green triangle. Of course, the health effects are very big if there would be no oxygen, as you could understand, because that would lead to immediate death. Normal atmosphere is 21%, and then you go gradually lower and lower, and we will come back to that also a bit later in the presentation. The consequences of these lower oxygen levels is, of course, the health. You can get dizzy and also lose conscience, but also a reduction of the oxygen level could make you perform the wrong decisions because of that. So what we then, of course, get is that you need to challenge somehow these two probabilities, both of fire and health effects, to find the right balance between them. Partly trying to lower down the oxygen to minimize ignition or preventing even ignition, but also having an environment which is okay for people to be in. And the area of interest, of course, which are in these systems and in this area is, of course, somehow between 10 and 21%, 21 normal atmosphere, 10% very close to the inerting levels needed. So that's a bit the challenge of the whole system or the design of the system. The principle of the technique also again is described in at least two major standards which talk about design, installation and maintenance. One is the German VDS standard on oxygen reduction systems, the VDS 3527. The EN is the English version. And then there, from about 2 years ago, there's an EN standard 16750, which is somehow replacing a previous British standard ASPE 95, which is a design and a standard at EN level. I'm aware there's also an ISO standard on development, but these are the two major ones which are referred to. Where is this system or this technique very interesting for us is in areas where it might be very difficult to use sprinklers. That means maybe very automated storage areas where there's a lot of complex and very compact storage areas, and where you, due to the fact that you want to do everything automated, it's very difficult to get everywhere with the sprinkler system. And there are also, of course, applications where maybe sprinklers are not at all possible, and that can be in very low temperature freezing areas. That's for clear. So on the left you see such a compact system where the materials or the goods are picked up from a kind of a wreckage storage. So that somehow is talking about the application of the principle and also about how it works. And I will give now the word to Brian, who will talk about fire prevention versus fire protection.
Thank you, Patrick. One of the objectives that we had from the outset on this project was really to try to look at the literature and understand what the objectives for protection of warehouse storage facilities would be, and where and how oxygen reduction systems would fit into the scheme. And so we looked first to the fire safety concepts tree to help us, look at the prevention side and to look at the protection side. And one of the things that we looked at is that you basically within the system have the opportunity to prevent the fire ignition, essentially to prevent the fire from occurring, or if you're unsuccessful in doing that, or in addition to that, you have opportunities to manage the fire impact. And so ORS systems could potentially work in both of these environments. So if you look at preventing fire ignition branches, if you follow down to the control of the fuel and control of the fuel ignitability, you'll see an area that is controlling the environment. So this is very much in the wheelhouse of the applicability of ORS, because the intent is to reduce the oxygen level such that you can't support ignition and potentially cannot support combustion. So very clearly ORS could be a very effective prevention system, within the operations of the fire safety concepts tree. If you look also, however, to managing fire impacts, which is the other major branch, you can control the combustion process, and again look at controlling the environment, and then you can have in this case kind of a chemical interruption of the process. And to a certain extent, many types of extinguishing agents, clean agents, work this way, where you could either interrupt the chemical process or you could reduce the ignition. So in a way, there is applicability on fire protection, but the other part of the fire protection in the management side is that we're dealing with managing the exposed. And when we're in a warehouse facility, obviously the contents are a big component of the protection, but most warehouse storage facilities also have people. And when you're thinking about the people component of it, Now you're getting into this situation of, when will people be in the protected space? What is the movement of people in and out of that space? How long will they be there? And what are the associations going on? So we need to think about those typing the objectives. And as Patrick had mentioned previously, there's this balance between fire control and health effects. And you can see that when you're dealing with a reduced oxygen environment at different percentages, then there's a different range of symptoms that could be impacted on people relative to the effects that it will have. So at very low levels, reduction of oxygen, there are no observed effects. Once you start getting down into the 15% range, there's been some studies that have shown some impact on night vision. Once you get lower, down in the 13% range, you have some increased breathing and heart rate. And then lower than that, you're starting to get into some physical and intellectual performance issues. And so once we started to get into that literature and we started to find out that there is quite a bit of research still needed on the medical side relative to the performance in warehouse, because a lot of the studies are people at altitude and so forth that don't necessarily take into account people that could be working in these environments. The other aspect that we have to think about and that we looked at is that in addition to fire safety legislation and regulation, there is also occupant health and safety legislation. And in many countries, there are requirements set in terms of minimum levels for either occupied or confined spaces that might limit, say, the minimum oxygen concentration from 19.5% down to perhaps 15%. And so you get this whole range of requirements, not only on the fire safety side, but the occupational health and safety side, which means that if you're going to use ORS and people will be involved, now you have to begin to have a range of personal protective gear and respiration devices and so forth. And so ultimately, when we looked at these issues and in discussion with the project technical panel, we decided that it would be important to focus on ORS systems for prevention rather than really getting into the details as a protection system because of the issues associated with the reduced oxygen concentration necessary to provide prevention of ignition without transferring over into negative health effects. And even so, if you're looking at the guidance documents, once you get even at 15% oxygen concentration, there are requirements that workers in those areas should have undergo medical exams and have limited exposure. There's concerns about, motor functions and cognitive abilities in these periods. You need to think then about signage, oxygen alarms, and different issues. And then what happens when a fire occurs and you might have opening of ventilation openings and so forth. So ultimately, given that there were many unknowns in this area, that clearly is identified as an area of future research, but then that puts us over into the range of really focusing on ORS for prevention, and we know that's really effective when the concentration is less than 10%. We're not so sure at higher levels, but that's again where additional research is needed. And with that, I'll turn it back over to Patrick to talk more about some of the operational performance issues.
Yeah, so if we talk about the performance limits, as Brian said, we are somehow at 10% at the lowest inerting level, and then normally 14–15% has been used. And if we look down, and you can see that on the table here, to some values, the range is somehow different depending on how you check that. We used the VDS standard, which at the moment of the study was available, and you see here in the table different ignition thresholds according to that standard, which was maybe one of the first issued standards, and you see that going from 11–12% for two of the alcohols to levels of 15–16% for a number of materials like PMMA, polyethylene, corrugated board, and PVC. However, if you look into the literature, for instance, from Xin and Khan from 2007, around the same period, you see that these are corresponding quite well for the two liquids, but for the PMMA and for the polyethylene and corrugated board, they're much lower. And that brings me a little bit to explain possible reasons for that. And and this is somehow the setup used in the VDS standard. It's also quite similar to the one in the EN standard, and it's used. You have a sample here, so when that is exposed with a very high velocity burner, which is at the moment I'll put it here, yeah. Which is a mixture of gas and oxygen, of course, and which has a quite high velocity, and the sample is exposed for that, let's say, torch almost. And the reason why you need, of course, oxygen in the flame, or to have a pre-mixed flame, is that you want to, of course, not have your flame holes or ignition source disappear. So if you look then an example of a test which we did in a previous study here in Lund, from the left to the right. This is just the same test setup. You see the very high illuminating flame, and on the left you see it attacking a particle board, and in the middle you see that the flame penetrates very well, very quickly, and that means that according to the test standard, that would be in many cases a pass, and these tests were performed at 21%. So there's some inconsistency in how to run the test, and also how to interpret a pass or a failure. And since the flame has a very high velocity, it makes in many materials very quickly a hole, and around that nothing then happens. So I will come a bit to that also later when we talk about, let's say, the need for how to define the test method. That brings me, in fact, a bit to task 2, where we look to the impact of reduced oxygen environments on fire hazard conditions. And in the report, there's quite an extensive amount of data on especially ignition behavior, but we decided to pick up here a few examples. So if you want to know more, I think the report is a good complement to this presentation. What is normally important for the analysis, or let's say when we talk about the different fire hazard conditions, of course, there's the ignition resistance of a material, how easily it ignites, the heat release, the amount of heat you can see on the picture on the right, where a cable tray is propagating, which is somehow a combination of the heat released and the possibility of ignited, but of course the flame spread includes also a lot of geometrical factors. One is very simply the orientation, vertically or horizontal. It makes a big difference. Then other parameters which can be important is smoldering of a fire, where maybe you want to see what that can lead if you have different, of course, oxygen levels. Another one is the mass loss rate, somehow connected to the heat release rate, but it's important and quite often also used in certain hazard assessments. And then let us say an important factor is that the smoke soot and corrosive development of the fire. So that means the smoke is important, for instance, for the visibility. Soot corrosive development is very important for possible functional performance of components, where they maybe will not work any longer if the soot is attached to it, or when the corrosive gases are attacking, for instance, the electronics. I must say in this presentation we only go to ignition and heat release ones, mainly because, which will be clearer later, is that we have a lot of focus on, let us say, the fire prevention in this study, and then the ignition is the, let's say, the major factor. If we generally look to common methods which we use, and I not want to go into details with a very large and medium scale test, but simple smaller tests where you maybe want to check these kind of parameters at small scale, then one of the very important and very known methods is the so-called traditional cone calorimeter, and I'm trying to see it a little bit more in the general research perspective. You all know that worldwide there are hundreds of test methods at small scale, but one which is used a lot for research and also for modeling is, for instance, one of the two we want to talk is the cone calorimeter. In the cone calorimeter, you have, as seen on the picture to the left, here a conical heater which exposes the sample, which is on a tray here, with a certain heat flux. Then there's an electrical spark igniter, which is not visible on this picture, which ignites the material. All the gases are collected in the hood, which is indicated by the arrow, and in the duct connected to this hood there is firstly a gas probe which takes parts of the gases to, for instance, oxygen analyzers, carbon monoxide, carbon dioxide analyzer, and possible other analyzer if you want to look into other gases from fires, like HCl, HCN, and so on. But the major thing is that we want to measure the oxygen, and the oxygen is connected to the fact that you, by the oxygen depletion principle, can measure or can calculate, sorry, the heat release of the fire. So and that's an important parameter. So you have firstly, or of course, already determined the ignition time, and then with the oxygen depletion principle you have the heat release. Here there's also a bit further on a laser system. In some other tests there are sometimes a white light system which allows us to measure the opacity of the smoke in order to make a link to possible visibility data. Finally, there's also here at the bottom a load cell which measures the mass loss of the sample. With all these parameters and all these measurements, you can do a lot of calculation and get a lot of important data out of this test. What is important, of course, that as you can see in this picture and also in the picture to the right here, is that the normal setup is done at 21% of oxygen, where you have traditional ambient air going into the hood. This method is, there's a lot of data on it. Of course, at 21%, it's a little bit less with respect to lower levels. But on the other hand, the ISO committees related to fire, ISO TC 92 Subcommittee 1 has a work item and they've done also quite a lot of research on that also, who puts the whole cone, and now I've drawn this picture into a box where we call this the cone calorimeter with control atmosphere, or CACC. There's still an electrical spark and there's still heat radiation, and I think that's the important thing I maybe did not mention in the previous slide, but the ignition in this test is determined with heat radiation or heat flux as external source. So you can go up to in the cone calorimeter up to 100 kilowatts per square meter. In the next slide, you see example of this box, which is in principle put under the same hood, and which you can see on the left. On the right, you see a sample burning into this box, and of course the box is fed with different, let's say, oxygen nitrogen mixtures, and then you can determine these ignition times. You can determine also with adaptive calculations the heat release of the sample. Let's look to some data, and we traditionally take a lot in PMMA as a reference, and I showed the data also in the table previously. In this graph, you can see here the red one, which is now indicated by the green arrow. This is the traditional, let us say, cone calorimeter test for a PMMA sample. If I remember well, it's a traditional 25 millimeter thick PMMA. And then you can see bit by bit that we see it's a little bit difficult to see that the ignition times changes, but you see that the heat release is lowering, and let's say the burning period on the other hand extending. And the one which is maybe interesting is then the blue one, where you can see that you still have this burning at around 10% of oxygen. It ignites much later, so that's a positive, but it's still burning, and then it's releasing a heat release, which in this case is indicated as kilowatts, but by some calculation you can also get it per square meter with the sample. You see also here some data of the levels where there is a threshold between igniting or not igniting, and you see that, and I think that's important to notice that if we look again to the PMMA here, that the limiting, let's say, option in this cone calorimeter, it reduces when the heat flux goes up. So you see here 15% of 15 kilowatts per square meter is 15% of oxygen. 30 kilowatts per square meter is about 13.8. So it's lowering, and I think that's something important to observe and to realize, so that the ignition behavior and also the as a consequence the heat release is changing and is getting though partially lower, but it's still existing at levels of 10% for PMMA if there's a radiance. The graph indicates, if I remember well, a graph of 25 kilowatts per square meter. So another apparatus which is common and quite similar to, let's say, the cone calorimeter is the NFPA, or the fire propagator apparatus, originally developed by Tucson. So it's called also sometimes a Tucson apparatus, but it's also both available as not only as an ASTM standard, but also as an ISO standard from the same committee which I mentioned earlier. Here the the test setup is a bit different. You have a number of 4 heaters. I think maybe they are better to see here. That's one of them, which is also radiative heaters, which expose then the sample which is in the middle of that. If you look to this, you see that there's a chimney, so that means that in the standard test setup from the FPA, it's ready, including that the flow around the sample is or can be controlled from, let us say, 0 up to an oxygen concentration as high as you in fact want. And that one, it's as you can see, a bit similar with a hood and a duct, so you can measure smoke and so on with that apparatus. And this apparatus have been used to supply the data which I earlier referred from XIN and CAN. What is important to mention also in this case is that this FPA apparatus gives the same results as heat release and mass loss rate, which can be seen on the picture. To the left is the heat release and mass loss rate for a PMMA in normal air. On the right, the heat release which is the more noisy signal, and the mass loss rate is given for PMMA in a reduced oxygen, roughly about 15%. And you see also in both graphs it's the same scale, so it's easy to compare them. The reduction of the heat release, but it still also ignites and produces a flame, which you can see in the top right picture, as that is an example of the test. So, and that's also the data produced by XIN and CAN from 2007. Finally, when we talk about hazards, I want to just mention as a kind of maybe rehearsal from the your earlier courses, maybe on fire chemistry or fire dynamics, is that for instance, the suit which is given here by the dotted lines and so on for different materials is increasing when the equivalency ratio also increase, and that's, in this case, it's given as the ratio of the ventilation controlled to the well ventilated yield. So that means that for the lower equivalency ratios, these are the same, and once you go to higher than 1, it's getting underventilated, as we also call, and then you see that the soot is increasing, while also, for instance, parameters like carbon monoxide increases. So when you get more and more into underventilated conditions, some of these factors which influence not only the production of carbon monoxide but also soot, and that means also impact of soot on components increases, and this happens then also when you use the oxygen in your test sample. So I just want to mention also one part of a test series which was done by FM, by 2NL, where they increased, let us say, the size to a medium scale setup. I've been focusing earlier mainly on small scale test apparatus, but the best way to investigate, let's say, the behavior of a system or a composite is to do it in at least a medium scale or a large scale, because the small scale test just pick up a part of the sample and you don't get all the details of the configuration. And they conducted a number of series which was produced a paper also last year, and we see that for certain, and this is the list of different type of classes of goods where the limits either hard or soft limit is depending on whether the igniter, which I maybe mentioned is in the test here at the bottom, is either continuously on or not. And again, the igniter here is gas flame or pre-mixed gas flame, and we see that these limits are again in the order of 11–13%, so somehow lower than what we have seen in earlier tables. And it shows that the limiting level for ignition depends a lot on your let's say, fire test scenario. That means heat radiation, type of ignition source, type of flamings, and so on. So I think this is important to realize that in reality that will be a lot different. So then now we'll go over to the task 3 was to identify impacts on real world application of these systems. And I will give you now also the word again to Brian, who will take this task.
Thank you, Patrick. Patrick just went through some of the testing issues, some of the fire dynamics and fire chemistry issues that are of concern relative to ORS, the fuels being protected, and the environment. But one of the factors that needs to be considered as well is the environment into which you're putting these systems and what potential challenges could be there. So there are a few considerations on the design side. One, as has been talked about, is what is the oxygen concentration level and the ability to maintain that level over the life of the system and the life of the facility. And so there are different percentages where different effectiveness can occur if you're down below 10% versus if you're in the 13–15% range and above that. You'll get different factors in terms of the effectiveness of the system in preventing the ignition. You also have to kind of think about the ignition sources, and as Patrick just mentioned, the fire scenarios. So could there be arcing type ignition sources or exposure fire ignition sources from adjacent spaces or other types of situations that don't reflect at all the very small test parameters and the test setup in the current standard. So if you have ignition scenarios that are much different than the test methods, you can't necessarily assure that you're going to get the level of protection that you are anticipating. And throughout the life of the building, this means that you need to have good controls on understanding what the actual oxygen concentration is in the protected space over time, and understanding, whether you have permeability of the enclosure compartments, how often are doors open and closed, are you taking into account, doors open for movement back and forth of goods, do you have issues with aging, with the containment of the facility, and so forth. And all of these need to be thought about in terms of kind of the mechanisms to maintain appropriate oxygen concentration over time. And going from the design side into kind of the review and long-term operation, you need to have a good sense of what the controls are, how the again the room tightness is monitored and maintained, what happens in terms of alarms that are given, how are you calculating the flow rates, how are you assuring that you're achieving the design concentration over time. In developing or having functional tests for critical components such as valves, such as sensors, and so forth would be particularly important. And there's some guidance on that in standards such as the UL 67377, which looks at the impact of of maintaining a safety integrity level for the space and having a test procedure to assure that all of your components are operating correctly. When we get to the inspection, test, and maintenance program, you need to have this laid out in a very detailed manner, and you need to have people undertaking the inspection and testing that understand what they're looking for in terms of these tightness issues, in terms of component reliability, performance testing of the different systems, visual inspection of valves, and so forth. So in some senses, this is not entirely different from ITM procedures for other systems, but it needs to be laid out very well and be very clear in terms of what is required, when, what needs to be looked at, how are you maintaining this condition over the life of the facility, how are you dealing with the normal operation, movement of goods, potential for ignitions, and so forth. And all of these are important factors when you're dealing with the warehouse situation. One of the things that we've also learned from every other type of fire prevention and protection system is that impairments to the system, for whatever reason, are often a reason for the system not being available when needed or not functioning at the level that it's expected to when needed. So risk assessments can be helpful with this. Again, UL 67377 talks about, for the safety integrity level of the safety function of the system, appropriate risk assessments and risk management procedures are needed. And these just all have to be built into not only the design side of things, but the operational management side of protecting facilities which are using these types of systems. The other aspect in task 3 is to think about, what the environmental concerns are with the operation of warehouses that might be difficult to address. And these are in many aspects very much related to the previous discussion, in that you're looking at whether the warehouse is occupied or unoccupied, whether people are moving in and out, whether it's completely automated type system, if people are moving in or out, or goods are moving in and out, how are you capturing that opening area and leakages of the concentration, the overall volume of the space, and for the volume of the nitrogen needed, and maintaining the concentration over time, permeability of the boundary, walls, ceilings, and so forth, and even the contents of the warehouse in terms of, do you have porous materials that may have trapped oxygen that if a fire occurs will participate in the combustion, or do you have completely inert type of materials being stored. I think what we found, again, from literature review, is that when you're into these automated warehouse facilities, when you have tightly compact storage and so forth, where having a gaseous type of a prevention system could be more effective than having a water-based sprinkler system, for example, on its own, then that's a good application. And looking at all these concentrations and maintaining integrity is good, but then not forgetting about what happens if a fire does occur and the fire service arrives, opens up all the doors to the facilities, introduces oxygen into the environment, changes the dynamics. So operationally, there are issues. Firefighting response, there are issues that need to be concerned. The actual construction and volume of the space is something that needs to be considered. And overall, just thinking about kind of a defense in depth approach, or layers of protection as it's also called, might be a good way to be thinking about the design given these various issues associated with being able to assure that you've maintained the concentration for kind of the life of the building and the duration of the event. So with that, I'll turn it back to Patrick to kind of bring it together in terms of some of the research needs that have been identified to be dealt with moving forward.
Okay, thank you, Brian. The last task we conducted in this study was to somehow identify research needs to bridge the gaps between current tests and also system functional reliability in the real application, which was also explained already by Brian. So the first items is the research and development needs with respect to the test methods to determine the level to be used. And the first thing, which is in fact very important, is that apart from a very specific paper which I mentioned earlier, there are very little data where the system has been tested, or where data is available on real scale fire scenarios, where you have a setup in real scale and you conduct that, similar to what is done for other systems to prevent fires and so on. And I think this is an important part, is that a test method reflects a specific set of conditions, but we need a real scale scenario to conduct, and that real scale scenario, is of course very much depending also on your application. So it's not a simple item to solve, but I think it's an important part of which has to be done. It's not also one where you have a lot of data, as I mentioned. Then it's also very important that the test method which we see on the right, or a simplification of it to the right, with which is mentioned now in the EN and the VDS standards, is a test standard which has been developed and with a set of criteria and so on. And what is important then is something which is in the guidelines, for instance, in ISO TC92. The Fire Safety Committee, is that when you want to develop a test, and in this case it's even a kind of a prescriptive test where you want to use that test for a design or an acceptance of a system, that type of test needs to be validated against a real scale or a full scale type of test setup. And I think that's important. And this, of course, is a bit connected to my previous statement, but developing small-scale tests, for instance, in ISO is TC92 without having a proper validation. That means how well does the results reflect the real scale result or behavior is important. And that brings a little bit to the fact that in the real world we will have very different ignition sources, and these different ignition sources also, of course, depend on well, we were really aware of that on the type of scenario you have obtained. In certain cases there will be very small possible ignition scenarios or sources. In others there will be quite a lot and a lot of variation. And I think that each of these ignition sources, like there's some documentation of at least 5 to 10 different ignition sources in one of the ISO standards, have specific properties. And this is important to check them, and these could be a strength to be used in any type of test method. And I think that's important also. And Another type of conclusions to that is that also the type of material or product is depending a lot on the result. We've seen a lot of data on ignition thresholds connected to, in fact, a specific material, but we don't often have real pure materials in a test setup, like for instance a warehouse. It can be furniture items, and furniture items contain of fabrics, a wooden frame or a steel frame will not be a problem for ignition, of course, but a wooden frame, but it also contains a foam inside the furniture, and all these aspects, and maybe a lot of other details. And each material is different, and either you're determined for each of them, but we've seen in many other applications that sometimes the combination of the materials is not giving the same result as somehow the case of the single material. So that's important, and this has to do also a little bit again to the let's say validation, which I mentioned earlier, that before tests are introduced. So we feel that somehow there might be a need for an alternative test method to be used, or a test procedure with existing test methods which also reflect not only this small flame ignition, but also possible high radiative sources, or even sources which somehow indicate that you can correspond them with electrical high energy arc ignition sources. Because they will have higher, let us say, temperature, and in other cases also higher radiation or heat flux to the material. And I think this is also again depending from scenario, and it depends again on a full risk analysis in the facility. And also talking about these ignition sources is that we've seen this type of pre-mixed gas burners, and yeah, in certain applications maybe there is somewhere a pre-mixed flame, but maybe not often in a facility like warehouses. So there are other potential ignition sources, and they are connected maybe to liquids or materials, cables which are ignited by high energy arc and then start ignite, because we have to realize the basic principles of flammability limits say very clearly that the flammability limits or the flammability range exceeds or increases when you have, for instance, higher temperatures, and that also applies then for this type of test. So, but we need more data. There's a lot of data if we just look on one example, and I know that we cannot be completely give all the details and the examples, but an example of a simple pool fire is that there's not too much data. There's a lot of data on different sizes, different configurations, and so on. But if we look into detailed behavior of these pool fires at different oxygen levels, the literature becomes immediately much smaller. And that's because we have, of course, always concentrated us a lot on the idea that we have fully ventilated fires in this case. So, summarizing a bit from this different points is that we really need further research on the required oxygen concentration which is needed for these systems. I think that's very important to realize, so that we cover really all the real scale scenarios and situations, and not one or two specific ones. So then, if we look into research and development needs with respect to the RS operation and the specific application of warehouses, is that there's much more data needed, and that has to be built up in historically is onto failure rates, reliability, and so on of the different components. The technique is new, So that means that we still not have enough data, but we have to gather this data in order to be able to do full risk assessments and reliability studies. There's also the need to get more failure mode analysis connected to then the need for determine appropriate industry standard inspection, test and maintenance programs and so on. I think we also need, or we felt that we need to get more information on operational costs for OS systems in order to aid benefit or cost-benefit decisions. As you can see in the picture, it's a balance between investment and the type of fire safety requirements you have. In certain cases, leakages can be very low. In other cases, it can be high, and we need to know much more the ways how to determine and to how they will affect then the results, especially how they would increase over time, so that it's not a design from the first step, but a kind of a definition of leakage over time. We also need to check the tightness of the volume, how to check that and how to determine that. As I said already earlier, reliability and availability is also important, and we maybe have to see, like with with old system, is what type of backup do we have. If the system does not work, we have the traditional 21% environment, and do we then have any other protection, and what would happen in that case? I think it's important. It's in this with this system also similar to other type of system. If other active fire protections like smoke and heat venting or sprinkler systems are used, how is the interaction? That would be beneficial. Is there a need to get this combination or not, in order to maybe to see that there is a backup? With warehouses, you also have the fact that you will move a commodity from the outside into the protected space. So in certain cases, in time, there will be diffusion of the oxygen-reduced atmosphere into the commodity, if that's possible. But maybe in certain cases it is not possible. So that means that you have a commodity when it is obstructed by maybe plastics and so on, but that if the fire is very locally and the plastic is disappearing or melting, then maybe you suddenly have an amount of oxygen coming into the area, and we'll have a local fire which maybe is increasing well. So we have to see a little bit how that can affect the final behavior of the whole community or the whole warehouse. So so we have to also to see how these tightness tests can be done for these large volume spaces, as I said. I saw that now my picture came suddenly, which is the famous opera house in Copenhagen. That brings me a little bit to the research development needs connected to planned and emergency interventions. The fire brigade at a certain moment has to do an intervention. What would help them, and what would happen if they breach the enclosure where the oxygen-reduced atmosphere is. So we have to see on how these two are connected to each other, because this is just a hypothesis. It is possible that the fire is maybe smoldering and so on, and then you open it, and then suddenly there's oxygen coming, and you can have a very serious situation. So I think it's important to look into that into your risk analysis again. So other research development gaps and needs we determined in the project is, and they are somehow we're on the borderline. What we looked into is, of course, this acceptable level for medical conditions. I think Brian showed the table, and the numbers are a bit different depending from the local legislation, but we also maybe need a lot more of medical data. We just pointed out that in our report that because we are not specialists in that area, that there's need for more data there. And it's not only about the health issue, which was indicated on in the table which Brian showed, but also the fact is that at a certain moment, if you have to do certain decisions or for certain action in the environment, how well do you do a correct decision when you're maybe influenced of a lower oxygen concentration? And I think there's data available from other areas, but we don't have any connection to this type of application. So we also said that we have focused a lot on, let's say, the fire prevention part, but if we look to more the fire protection part, is that if we anyhow have a fire, what will happen with the spread? How well will it be reduced or not? And that is depending again on the oxygen level. And we need to know much more data on burning rates and heat release based on material and storage arrangement in these different oxygen concentrations, so that if we really have a fire, what happens. And this is very critical if you choose a level of oxygen which is too close on the borderline, that when the conditions of the ignition source or is somehow higher, or you have always a certain uncertainty of your test results, is that you can then get that fire, what will happen then? And we also then have to see what are the damage criteria to be studied in that case. So I think that somehow brings me to the conclusions, which is given in 2 slides. They are somehow repeating the items we mentioned earlier. Of course, we had a lot of focus on ignition, but it was not limited to ignition prevention and the associated test methods. So we looked into other aspects, as you have seen in this presentations. So we know that the factors such as preventing further ignition or controlling extinguished fire-induced oxygen environments really needs also further study in order to be applied to all kind of applications and also warehouses. I've mentioned already the test methods which are now in the EN and the VDS standards offer for us not yet convincing sufficient to cover real scale scenarios, and that there's considerable research needed to further develop test methods through also a number of full scale tests where we look into real application and real fire scenarios. I think this is in analogy what we have in other like ISO committees procedures before we introduced test methods. The task 2 gave a lot of information on the impact of reduced oxygen on heat release, smoke production, etc. As I mentioned also, the positive things are, as we could see, increases the ignition time, it reduces the heat release and so on, as long as when you have a fire, when you want to determine the threshold values, in case there is a fire, which we looked only into detail because we wanted to focus on fire prevention, there's of course smoke at reduced oxygen levels and at rather high equivalency ratios. It means more soot and more gas productions. We feel also that there's need to test actual products and systems to be investigated. Much is focused on materials. Pure materials are not always the only type of materials into warehouse. It's very complex products with different materials involved in it. and they are sometimes also very complex in what respect to the system, how it is, for instance, mounted or produced. In task 3, we revealed that reliability of the system should still be further investigations, and that we have to do research to build up a robust system which is easy to inspect and to maintain. And then I already mentioned we need more research in by health specialists down to what is acceptable health levels, so that we get some kind of more guidance there. What we have seen is that there are still little data available on, let's say, benefits, downside when really a fire occurs, despite the reduced oxygen atmosphere. So when there is a real fire, what is this then a benefit, or what happens really with the fire propagation and the fire development? So this is somehow the last slide with the conclusions. I want to acknowledge NFPA, also the PRG group, who was the support for this project through the Fire Protection Research Foundation. And I also want to mention the Swedish Board for Fire Research, because we did quite a lot of the preliminary studies before this project in a project supported by that board. So that brings us to the questions of this session. So thank you very much for listening, and if there are any questions, we can try to ask the moderator somehow to summarize the all the scrolling of different comments.
So this is Brian. I'll jump in a little bit. The moderators have put a couple of questions or tried to summarize a few things, and one thing that there's been a lot of discussion about whether or not there are real case studies and some on the volume of the spaces and so forth. And one thing that we want to clarify is that, you know, the scope of the project was a literature review, and what we had to rely on was material that we could find in the literature search. And I think one or more people have commented in the discussion forum that there's a lot of industry experience, but not a lot of case studies out there. So as a literature review, the aim was to identify, you know, system operation, how the test method worked, what the operational considerations would be, and what would require further research. And that's how the report was structured forward. So we just wanted to clarify for everyone that, you know, what we found were a lot of unknowns relative to information that's readily available in the literature. And that's one thing that was kind of talked about throughout, you know, Patrick's concluding remarks, is that there's a lot of areas that additional information would be very beneficial for not only better understanding system operation in practice, but being able to address some of these issues of different fire scenarios and so forth.
Excellent. Thank you very much. I believe there are a few questions in the presenters chat if you'd guys like to address some of those.
Yeah, it's Patrick here. I think maybe I can. I saw there was a question on the fact that on the ignition sources, and I think it is correct that there are, depending on let's say the application, maybe much more than just the radiative and the electrical ignition sources like chemicals. So I think the person who asked that question, I can agree with. There's much more, and that's exactly what we want to say, that apart from a small flame, there's a lot more than just this ignition source, and that we have to look in. I think that covered one of these questions. So I'll ask my co-presenters maybe to pick up after me and select another question to answer.
This is Amanda from the Research Foundation. I'll just jump in. I think Brian covered a bunch earlier, generally talking about the scoping of the issue. I did see somebody asked about the next steps related to research, and at this point, this literature review is available. I provided a link here in the chat if you want to check that out. And at this point, we don't have another phase lined up yet. Of course, there's a lot of gaps there, so if there's interest, we'll of course try and fill those in. But at this point, we don't have an active project.
Well, thank you to Brian, Martin, and Patrick. Much appreciated. Excellent presentation. And thank you, Amanda, as well. If you have any further questions or comments, please feel free to email them to custserve@nfpa.org. For more information on NFPA's upcoming webinars, you can view those at nfpa.org/webinars. And a recording of this webinar will be made available. You can expect an email with a link notification when it has been posted. On behalf of the National Fire Protection Association, the Fire Protection Research Foundation, the presenters, and myself, thank you for joining us today.